Hey there, method students. In this video, we're going to introduce the idea of continuous random variables and their probability distributions. So when we think about continuous variables, and it's important to make the distinction between, I guess, what we've previously been studying, which is discrete random variables. Well, discrete random variables are things that we typically count, right? So there's usually like a fixed, I guess, amount of values that they can take, because often you're limited by the fact that they might be like whole numbers if you're, say, counting the number of red cars that you see every hour. However, a continuous random variable, or a continuous variable more generally, is something that can actually assume any value over which it is defined. And that's because continuous variables are measured. So think about things like time or height or temperature. And in theory, these can take any value because you can measure them to more and more degrees of accuracy, right? So someone can be 152 centimeters tall, but you could measure it to more accuracy and say that they're 152.735 centimeters tall. And you can measure more and more and more accurately. So in theory, there's any sort of number that these values can take. And just as a bit of an introduction here, let's think about a histogram, so like a graph of the weights of 500 people, right? So weight is something that's measured, so that's a continuous variable. If we kind of put that on a histogram, it might look something like this one here, where, say, along the x-axis here, and it's not all labelled, but, you know, these might be the weights. I think if I can count properly, you know, this might be like 72 kilograms and 73 and 74 and 75 and all the way up. We've got a couple of them labelled up here. You know, this one's labelled 83, right? This might be a histogram that's showing how many people out of these 500, you know, weigh 72 kilograms, and how many weigh 73, and how many weigh 74, and so on. And it's showing, you know, that the distribution of the weights. Now, the bar that's highlighted there would represent the people who weigh 83 kilograms if we've rounded to the nearest whole number. But I guess if you're being really more accurate about it, you'd say that it's representing the number of people who weigh between 82.5 kilograms and 83.5 kilograms, because we've rounded it to the nearest whole number. But I guess in theory, and this is where what we start to get to in this chapter, if we were to get our measurements more and more accurate and make these histogram bars thinner and thinner, so rather than just round to the nearest whole number, maybe we had intervals of like 0.1 kilograms or 0.01 kilograms. If you imagine these histogram bars getting thinner and thinner and thinner, well, then actually what's going to happen is that instead of getting this sort of step-by-step shape to it, you would eventually get a smooth curve, right, that we could actually model with a function. And so that would mean that if you're looking at, say, you know, wanting to know what proportion of people weigh between 82.5 kilograms and 83.5 kilograms, instead of having this rectangular bar highlighted, you'd actually have an area under a curve. And that would involve, or finding the area under a curve, we know involves integration. And in this section, we actually use lots of integration, even though that might seem a little bit backwards to you because we're moved on to probability. So I've probably jumped ahead a little bit here. Let's just read through the theory first. So we're saying that if you've got this function, some sort of curve or linear function, they can be linear, that's modeling, you know, a histogram or modeling a distribution of data, well, a function f that is used to model the histogram is called a probability density function. And as I said just then, once we're dealing with a function, we can actually determine areas under the curve using integration. So what we're really doing is like finding the proportion of, or the percentage of, in this case, the percentage of people who might weigh between, you know, one amount and another, or it might be the, you know, proportion of people who are a certain height, or a proportion of things that take a certain amount of time, right? So anything that's measured, we can kind of use this idea of areas under a curve to find percentages of a distribution. And so in general, what we say is that for the continuous random variable x with the density function f, the probability that our variable is between two particular values, right, is going to actually equal the area under the curve between those two values. In other words, it's the integral of the function from a to b. So if we want to know the probability that our variable is between a and b, then we integrate the function from a to b. And so coming back to our example with this histogram, and say we wanted to work out the percentage of people who weigh between 82.5 kilos and 83.5 kilograms, well, if this function is called f of w, and it's a probability density function, then to find the percentage of people who weigh between those two values, we would actually just integrate the function over those two values, with those values as our lower and upper terminals. So that's the kind of the big idea in this section, right? And it takes a bit to get your head around, but I guess as you practice more and more examples, you will get the hang of it. And in general, there's kind of these two conditions that have to be satisfied for something to be a probability density function. And that is, one, that the function can't have negative values. So in the interval that the function is defined, all of it's got to be above the x-axis. And the second one is that the function, if we integrate the function over negative infinity to infinity, or in other words, if we integrate the function over its full range of values, then the total area under the function has to equal 1. That's really just like saying, again, go back to this histogram example with people's heights, that if we actually like found the area under the whole distribution, well, that should kind of show us 100% of the people in this example, right? So 100% of the distribution's got to be got to come out when we integrate for the full over the full function. that's a bit like saying that the sum of all probabilities has to equal 1, right? It's just saying that the whole distribution, when we add it all together, has to equal 1 or 100%. So these are the two big ideas when it comes to continuous probability and continuous random variables. All right, let's start having a look at some examples of how we actually can kind of establish those facts, but also how we can go ahead and find probabilities once we're dealing with these probability functions. So here's an example. We're going to consider the function with rule f of x. It's got this sort of hybrid function notation here. We've got a rule for the function if x is between 0 and 1. And the function equals 0 sort of for all other values of x. So our first job is to sketch the graph of f. And so I'm just going to sort of label it as part A there. So this function, well, I mean, that rule there we can see is going to be a negative parabola. I might actually just quickly expand those brackets just so we can kind of, I'm going to put the x squared term first, just so we can see quickly what type of parabola that's going to be. So a negative parabola with a dilation factor of this 3 on 2, and also it's shifted up by 3 on 2 units. So if we were to set up a graph here, and we haven't got heaps of room, so we'll just do it as accurately as we can. The graph would kind of, go something like that. And I'm just doing that faintly there because we've obviously got this sort of set domain of x is greater than 0, greater than or equal to 0, but less than or equal to 1. And so what I'm going to do here is I go, well, I kind of know that this turning point is actually going to be where the graph starts, and I know from the plus 3 on 2 that that point's going to be at 0, 3 over 2. And I know I'm sketching over here to the right-hand side. I want to go up to where x is equal to 1. So I might just say, well, let's work that out. When x equals 1, y equals negative 3 on 2 times 1 squared. So obviously that's just going to become times 1 plus 3 on 2. And that's going to give me y equals 0. So actually when I sketch this function, I'm really just sketching it from here to here, where this point is 1, 0. And that the rest of that sort of dotted line that I drew in there, that can just go away. All right. Now this point's important because what we've done here is we've sketched really the vital part of the graph. We've sketched this rule here, but this question actually said that f of x is equal to 0 if x is greater than 1 or if x is less than 0. So even though this seems a bit redundant or easy to forget, I suppose, you actually have to sketch that. So if you think about the line y equals 0, that's just going to be a horizontal line that's on the x-axis. So I actually have to sketch that and show that it's there, right? And so from here, for x is less than 0, the graph of y equals 0 would just look like open circle here, and then a line going across. So there's really 3 parts to the graph. Even though the parabola seems like the most important bit, we also have to include those sort of y equals 0 parts on either side of the parabola that we've drawn. Okay, so that's the graph of our density function, our probability density function f of x. Next part says show that f is a probability density function. So for part B, what we want to show is those 2 features that were on that first page, and those 2 features were, 1, so show on the camera there, that the function is greater than or equal to 0 for all x. Okay, so you can't have any negative y values on the graph. And 2, that the total area under the function for the whole interval that it's defined would equal 1. Okay, so basically, I guess we can satisfy that first condition by looking at the graph, right? So we can say that from the graph, f of x is greater than or equal to 0 for all x. And the second condition was that the integral of the function, now in the sort of the theory or the rule it says from negative infinity to infinity, but if we think about this as like area under a curve, well obviously all these parts of the graph that are under y equals 0, they're not producing any area here. There's no area between the function and the x-axis for this linear part and that linear part. All the area is under here, right? So instead of trying to integrate from negative infinity to infinity, actually what we're going to do is integrate from 0 to 1, because that will capture all of this area. And what should happen is that all of this area equals 1. That's what we're trying to show here. So when we integrate the function from 0 to 1, and again, I'm going to use, just because it's probably slightly easier to differentiate this expanded version of the function, so I'm going to use this rule here. So the integral of negative 3 on 2 x squared plus 3 on 2 with respect to x. We're trying to show that this should equal 1. So let's anti-differentiate it. Add 1 to the power, divide by the new power, so that will give us negative 3 on 2 x cubed. Oh, I've made a mess of that. Divided by, put that there, so divide by the new power. So we'll get some cancelling there with a 3 on top and 3 on the bottom. And 3 on 2 becomes 3 on 2x on 0. Okay, so that will equal, like I said, we've got some cancelling there. X squared, negative x squared on 2 plus 3 on 2x. All right, so when we sub in our terminals here, we get negative 1 on 2. So when we sub in x equals 1, that is, plus 3 on 2, minus, and when we sub in the lower terminal 0, both of these terms have got x's in it, so they're going to become 0 plus 0. And so this first bracket, well, that's going to give us negative a half plus 3 on 2, that gives us 2 over 2, which of course equals 1. All right, and so for part B of the question, those are the two conditions we've shown. We've shown that the graphs, or the function is greater than or equal to 0 for all values of x, and we've shown that the integral, the total area under the function, is equal to 1. So they're the two conditions satisfied, and that's how we've shown that f is a probability density function. And so for this last part, it says find the probability that x is greater than 0.5. So probability that x is greater than 0.5. Now essentially what we're saying here when we look at the graph is, okay, well we know that this is 0, we know that this is 1, so 0.5 sits here. And the probability that x is greater than 0.5 is just all of the area under the function where x is above 0.5. So it's essentially all of this area here that we're trying to find. Okay, and so again, key idea in this section is that the probability will be given by the area under the curve. So we have to antidifferentiate from 0.5 to 1, this function. So the antiderivative of 3 on 2x squared plus 3 on 2 with respect to x. We already worked out the antiderivative before, so we know that the antiderivative is going to be the same. It's just the terminals that are different. Okay, so we go, actually, I can kind of just use a bit of a shortcut. I might actually just use that antiderivative that's already written there, partly because I'm running out of space. And the upper terminal is actually the same as what we did in part B. So I'm going to jump straight to subbing in the upper terminal, which was negative 1 on 2 plus 3 on 2. This time, though, when we sub in the lower terminal, we're not just going to get 0 plus 0. We're subbing in 0.5 into this antiderivative that we worked out before. So it's going to be, 0.5 cubed over 2 plus 3 over 2 times 0.5. Oh, that's a fair bit of mess, and I don't have much room left, do I? Anyway, let's do the best we can. So that first bracket's going to be 1 minus, now, okay, so this is going to be, I'm going to do a bit of this in my head because I don't have space to write down too much working here. Think of the 0.5s as a half, probably makes it a bit easier. So a half cubed would be 1/8, and then 1/8 divided by 2 gives me 1/16. Plus 3 on 2 times a half, well that would be 3 on 2 times 1 over 2, so that gives me 3 over 4, so plus 3 over 4. Excuse my working here, this is getting pretty messy. So that's going to be 1 over 16 plus 12 over 16, so that's going to be 1 minus 13 over 16, which will equal 3 over 16. Okay, so the probability, in this case, the probability that x is greater than 0.5, remember that's represented by this area here on the graph, is going to be equal to 3 over 16. And if you have the graph, it's always good to do a bit of a common sense check, right? Remember, this full area would be equal to 1, and clearly this sort of section of area that we're finding is less than half of the full area. So we probably could have estimated that the probability we were finding would be less than a half. So 3/16 looks like a reasonable answer. Might pause out there and then go to another video to go through the rest of the examples because they take a little while, these ones.